In this video, you will be learning about projectile motion so that you can assess and reconsider your life choices. Maybe you would like to be a human canon in the future for your job. Just kidding. Of course, our learning targets for this lesson is you have to be able to define what projectile motion is, give examples of objects that are in projectile motion, and then, of course, you have to be able to recognize the variables in a projectile problem because that will serve as your springboard before we proceed to the video wherein we're going to solve actual projectile problems. But before we begin, I have here a physics puzzler that I want you to try answering using your wild guess or prior knowledge. So it says here two baseballs are held at the same height. One is dropped straight down while the other is thrown horizontally at the same time. Which ball will hit the ground first? So feel free to pause this video at this point and then take a guess. Maybe you write down your answer on a piece of paper because in the middle of this video, I'll be revealing the answer to this question and provide explanations as well. So again, one is dropped straight down, the other one is thrown horizontally, and that happens simultaneously. So which will hit the ground first? Now let's dive into the lesson. So first, the definition of a projectile is as simple as this. So it's a body that is given an initial velocity and then follows a path determined entirely by the effects of gravity. So take note that it doesn't necessarily mean that gravity is the only thing that affects a projectile or an object in projectile motion. So we also have air resistance because obviously when you throw something in the air, when you give it an initial velocity, whether it's a ball or whatever it will be affected by air resistance at some degree. However, for simplification of the analysis in projectile problems, we're only going to consider the effects of gravity, or at least we're going to assume that gravity is the only factor with significant effects on a projectile. So in comparison to air resistance, definitely gravity has much more significant effects as a force. So that's the only thing we're going to consider when we analyze projectiles. So some of the examples of projectiles are batted baseball, thrown football, bullet as well, and including some of the illustrations we have here as well. So we have golf ball, even a bullet is considered as a projectile. And even these Angry Birds, if you're still familiar with this old game, I used to play this one. Yeah, so also you might encounter the word trajectory quite often. So do not be intimidated with this kind of term. So trajectory, for example, simply means or simply refers to the path that is followed by a projectile. And we're going to analyze a projectile's trajectory in the latter part of this video. And then last point I have to make, the analysis of projectiles in this lesson or in this YouTube playlist will be based on an idealized model. It's also the same thing that you're doing in your high school class or maybe college physics. So meaning to say, when you say idealized, we're going to ignore the effects of air resistance as well as the curvature and rotation of the Earth. So that is for us to attack these projectile problems much easier. Definitely, we're still gonna get pretty good accuracy for the problems we're gonna analyze. It's just that we need to limit the problems, and as you probably encounter in most physics textbooks, we only consider objects that really can ignore the effects of air resistance. Example, golf ball, bullet. Those things can easily ignore the effects of air resistance. They're not significantly slowed down by air resistance, and they can also ignore the curvature and the rotation of the Earth. So we're not going to consider objects like, say, for example, skydiver, because a skydiver uses a parachute, and a parachute can be easily affected by air resistance compared, for example, to a bullet or a golf ball. So that's why these things are often used in physics problems. But another thing, for example, a long-range missile, for example, it cannot easily ignore the curvature or rotation of the Earth because a missile will travel much farther than a golf ball, for example. So in that case, a long-range missile cannot easily be analyzed as a projectile because the curvature of the Earth will be significant for long-range missiles and other similar kind of stuff. And for that reason, because of these assumptions that we have to make for an idealized model to be analyzed more easily, will be restricted to objects that are that can really ignore the effects of air resistance and curvature of the earth. That's why most physics problems on projectile involve baseball, soccer ball, golf ball, volleyball, and many other kinds of balls. Yeah, so not just balls, of course, even rocks, pebbles, and other things that do not travel that far and are not significantly slowed down by air resistance. So next, we're gonna analyze the motion of a projectile. So the purpose of this is for you to like easily approach physics problems involving projectiles. So first thing we have to notice that we have here a parabola or a parabolic trajectory because that is how the motion of a projectile looks like, or that's how the motion path of a projectile looks like. So first point we have to make, always remember that a projectile is in two-dimensional motion, meaning to say it is moving vertically. There is a vertical displacement, and there's also a horizontal displacement. And it might sound intimidating for some, especially for high school students, because you're used to one-dimensional motion. So you're used to one-dimensional kinematics, like there's only either horizontal or vertical motion. But take note that there's nothing so intimidating about projectile because it's just a combination of what you have learned before about vertical and horizontal kinematics. So we're just basically gonna combine our knowledge of both. So it's something that should come easier for you, especially if you have a good background with one-dimensional kinematics. And then also take note that in the horizontal axis, the projectile is in constant velocity motion because we ignore air resistance. That's our idealized model. And then that means to say that when you are analyzing the horizontal motion of a projectile, take note that the acceleration there is zero, meaning to say there's no change in the velocity of a projectile along the x-axis. So when you launch a projectile, for example, whether it's a golf ball or soccer ball, whatever it is, whatever is the horizontal velocity of that projectile, it will be the same all throughout its entire trip. And that is represented by the equal length of these arrows because as time goes by, the horizontal velocity remains the same for our projectile. And then what else? Another point that we have to make here, as opposed to the horizontal motion, take note that the vertical motion of a projectile is in constant acceleration motion due to the Earth's gravitational pull. So, meaning to say, going upward, to be more specific with that, going upward, the projectile is actually slowing down in terms of vertical velocity or v sub y. So that is because when something is going up, of course, it is opposed by the gravitational pull, which is downward. So it will slow down until at the very top, when it comes to the top, the vertical velocity becomes zero. So there's a momentary stop at the top of the trajectory, and then it goes back down. So take note that going down, the vertical velocity increases, or the object speeds up in terms of vertical velocity because it favors the direction of gravitational pull. So going up, vertical velocity decreases, and then going down, vertical velocity or v sub y increases. Okay, so that's the effect of gravity on an object. But again, v sub x or horizontal velocity is constant throughout the times of 0 second, 1 second, 2 seconds, 3 seconds. The horizontal velocity is constant. Going forward, as I mentioned earlier, at the top of the trajectory, a projectile's vertical velocity is zero. Again, because gravity will slow it down until the vertical velocity becomes zero. But take note, a common misconception, some students think that the vertical acceleration also becomes zero at the top, but that's not quite true because even at the top of the trajectory of a projectile, gravity is still acting. So, meaning to say, the object is still going to change its velocity. So, going down, what will happen then is the object will speed up by 9.8 meters per second every second. So, that's what's happening there. Because gravity won't stop acting on it even if it gets to the top. Yeah, so that's it. Another point we have to make. So, again, acceleration along y is equal to negative g, or negative 9.8 meters per second squared. And then take note, throughout the entire trip, again and again, your horizontal velocity is constant, as shown by the constant length of all these horizontal arrows. And then take note as well that the velocity of a projectile, which is the actual velocity in the actual trajectory, it's going to be the vector sum of the vertical and horizontal components of the velocity. So if you've studied vectors before, we're gonna use some trigonometric functions, if you remember them, for us to like solve for one thing using the other. So example, the problem is asking you to solve for velocity, and then you're only given, or you only know v sub y and v sub x. You can definitely work that out using trigonometry. So make sure that you still have a good grasp of your lessons on vectors as well as trigonometry, because they will come in handy when we get to the problem solving part. So that's it. Key takeaway, make sure that you know that the trajectory of a projectile is a combination of the horizontal motion with constant velocity or zero acceleration, whereas the vertical motion has constant acceleration, meaning to say the velocity is changing at a constant rate, and that's negative 9.8 meters per second squared. Okay, going back to our physics puzzler, let's see if you got this right. So again, two balls are held at the same height. One is dropped straight down, the other is thrown horizontally at the same time. So which ball will hit the ground first? Okay, the correct answer is tin, 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 tin. They will actually reach the ground at the same time. I'm not sure if you got that right, but most oftentimes when students make a mistake answering this question, they will actually think, or yeah, they would actually think that this horizontally launched one hits the ground first. But maybe if you're wondering why, how come they will reach the ground at the same time? So the explanation is simple. Number one, take note that the other one is dropped, so its initial vertical velocity is zero because you didn't push it downward. On the other hand, the second ball, will you only give it a horizontal velocity? Meaning to say maybe you pushed it sideways or whatever. Maybe you hit it with something. But it's sideways, it's horizontal. So you didn't give the second ball a vertical push either. So you didn't give it an initial vertical momentum. So they're actually given a fair starting position or fair starting velocity, which is 0 meters per second vertically. And whatever horizontal push you give on the second ball, it's not going to help it progress along the vertical axis because it's a horizontal push, okay? And vertically, they will still accelerate at negative 9.8 meters per second squared. So yeah, they're moving at the same time. I mean, they're moving equally fast throughout the different time intervals because you are giving them 0 meters per second for their vertical velocity. So again and again, the horizontal velocity that you imparted on the second ball does not affect the vertical motion of this object, which makes sense, right? I mean, if you give it a horizontal push, how can that horizontal push help this object get to the ground any faster than the other one if it's a horizontal push, right? So the only way for the second ball to like get to the ground faster than the first one is if the push you gave it is downward. Example, you lurch it downward rather than just merely dropping it or pushing it horizontal. So yeah, they're gonna reach the ground at the same time. So what, Miss? Will it make me as wealthy as Elon Musk? Well, definitely no. But take note that concepts like this will help you analyze physics problems more accurately because you're gonna avoid common misconceptions, and therefore you're much less likely to make a mistake when you set up the equations or when you analyze or answer conceptual questions as a whole. This one is just basically a screenshot or a view of how the balls are positioned at a different time intervals throughout the dropping action. So that's it. Again, they're gonna reach the ground at the same time. Now we're going to proceed to the three cases of projectile motion. And it's important for us to be aware of these three cases because there are some variables that are known for every type of, or for every case rather, of projectile motion. And they can help you with the problem solving part later on. So first we have case one, horizontally launched projectile, which looks like this. So maybe it's a diver running on the top of this platform and then ending here towards the water. So it can be like that. Maybe it's also a stunt rider in a motorcycle that's moving on top of a ledge and then it goes back down. Take note that for this case of projectile, initial vertical velocity or V not Y is 0 meters per second because you're not giving it any downward push or upward push. All the momentum that starts this projectile in motion is just horizontal. So this is a case one projectile. So take note as well that when you encounter a case one projectile problem, the velocity given in those word problems is the v sub x, horizontal velocity. So they will not necessarily directly say v sub x is this. So you have to be well aware when you read a problem if it is a horizontally launched projectile by imagining it, by sketching the problem. Because if you realize that, you'll know automatically that one implicit given there is b not y, which is 0 meters per second. Next, we also have case 2 projectile, which is a projectile launched at an angle. So for case 2, however, specifically, we are referring to that kind of projectile that has the same start and end points. And not the same, but they're of the same height, meaning to say, the starting point and the end point are equally high, and that's case 2. And then in this kind of problem, usually, guys, the velocity given is the velocity along the actual trajectory. So meaning to say, for case 2 projectile, they will give you a velocity. They will not say if it is horizontal or vertical. And in that case, it's referring to the velocity of the projectile in the actual trajectory. So it is a diagonal vector if you're gonna represent it vectorially. Also be careful, it's also possible for a case 2 problem to give the vertical velocity, for example, or the horizontal velocity. Yeah, but if it doesn't specify if it is vertical or horizontal velocity, it would be safe to assume that the velocity they're giving you is just simply v, not v sub y nor v sub x. And v is referring to the actual velocity in the actual trajectory or path. And then that's v. And then v sub x would be this. It's something you can resolve using some vector equations. And then v sub y is represented by this upward arrow because the vertical velocity will be pointing up for this part of the trajectory. And then take note, if you need to know v sub y or vertical velocity, you can use v sine theta to solve for v sub y. And in some physics problems, you need to solve for v sub y. And then, yeah, take note again that v is the actual velocity in the actual trajectory. And then theta is the angle between the velocity vector and the horizontal axis. And then for v sub x, you have v cosine theta. So yeah, sometimes the projectile problem would necessitate that you solve for v sub x, and you can solve for that using v cosine theta. Another thing is that the final vertical velocity is equal to the negative of the initial vertical velocity. So that is assuming that the initial vertical velocity you're referring to is the one upon launch of the projectile. And then the final vertical velocity is the one before it hits the ground. So why is that so? Why do they have the same magnitude, and why is it negative? So on and so forth. So the reason is because if you launch a projectile, its initial vertical velocity is actually decreasing by 9.8 meters per second every second as it goes up because of the opposing effects of gravity. But take note that from the maximum height of the projectile, it actually goes down, and because it favors the direction of gravity, it will actually peak up 9.8 meters per second every second. So imagine that going up, you lose 9.8 meters per second every second, and then going down, you pick up or you gain 9.8 meters per second every second. So basically, whatever is the initial vertical velocity, yeah, you're gonna lose it, you're gonna decrease its value going up, but you're gonna increase its value again at the same rate going back down. So what you lose along the way, you gain it back on your way down. And take note that the final vertical velocity is the negative of the initial vertical velocity because the final vertical velocity is actually downward in terms of direction. So it will be the negative of whatever is your initial vertical velocity. And please take note that that's a good information because sometimes maybe you can encounter a multiple choice problem in an exam in projectile motion, and then it asks you about the final vertical velocity, and then, well, if you know the initial vertical velocity, as long as it's case 2, as long as it's of the same starting and end point level, and they're going to be equal in terms of magnitude. So that's a quick way to like deal with that kind of question rather than actually solving. So yeah, that's it. That's an important tip to remember. Also take note that I just clarified that the initial and vertical velocities in this scenario are these specific 2 points because in reality, when you solve projectile problems, the initial and final velocities could be whatever points you choose. But in this equation that I'm giving here, I have to be very specific that I'm referring to the initial vertical velocity, which is upon launch, and then the final vertical velocity I'm referring to in here is the one before it hits the ground. And then lastly, we have case 3 projectile. So it looks like this. It's actually quite similar to case 2 because it's also launched at an angle. However, instead of having the same level or height for the start and end points, in case 3, we have two different levels for the starting and end points. So as you can see in here, the starting point is actually higher than the end point of this trajectory. However, take note, it's also possible to have a case 3 that looks like this. So as you can see, it's also launched at an angle. However, you can see that the starting point is lower instead of higher compared to the endpoint of the trajectory. So sample scenarios, perhaps basketball, and then those carnival games where you have to throw stuff and then hit some stuff toys or whatever items that you can win as a prize. That's one. Another possible scenario is like when Romeo throws some pebbles on Juliet's window. Too mushy for an example, but that's another case 3 example. So for this kind of problem, yeah, the same equation still applies. If you are given the velocity and the actual parabolic trajectory, you can solve for v sub y and v sub x using these equations. And then again, if the problem for a case 3 projectile does not specify if it is a horizontal or vertical velocity that they are giving, then it's safe to assume that the velocity they're presenting is the velocity along the actual trajectory, and that's v, okay? It's neither v sub y nor v sub x, but from v, again, you can solve for v sub y and v sub x using these equations. So that's it for the 3 cases of projectile motion. Next, we're going to proceed to the equations that you will encounter in projectile motion and that you're going to use when solving projectile problems. First thing, I want you to notice that we have this table and it's divided into 2 columns, so horizontal and vertical. The reason is because we have different sets of equations for x component and y component, simply because horizontal motion of projectile is not accelerating, it's constant velocity. But for vertical motion of a projectile, it's accelerating uniformly. So take note that for horizontal motion of a projectile, this is the only applicable equation. Apart from this, so it's v sub x, or horizontal velocity, equals displacement along x over time. But for the vertical motion of a projectile, we have these constant acceleration equations that you've encountered before when you studied freely falling bodies and horizontal UAM. So these equations are still at work because for the vertical component of a projectile, we have uniform acceleration due to the effects of gravitational pull. So we're going to use these equations. Don't worry, they may look intimidating, but I think it's just because of the subscripts. But the equations are quite simple. You just have one plus sign in all of them and just a couple of multiplication operations. It looks a little longer because of the subscripts, but those are just to indicate that these apply to the y component of the projectile. So you have the subscript y, for example. And then this is sub-zero, meaning to say initial vertical velocity. V sub y is final vertical velocity. We also have these equations I've shown you before, because if you are given the velocity in the actual trajectory, which is v, you might need to solve for v sub x and v sub y at times. And yeah, just to elaborate and clarify that further, again, these equations, the v in the equation is referring to the velocity in the actual trajectory of a projectile. So it describes how fast the projectile is moving in the actual trajectory. And then the v sub x is represented by this horizontal arrow. It represents how fast the projectile moves along the x-axis. And again, v sub x is constant throughout the entire trajectory. And then lastly, we have the v sub y, which is represented by this green vertical arrow. It's a representation of how fast the projectile moves along the y-axis. And again, v sub y is changing because going up, the projectile slows down due to the opposing force of gravity. But going down, v sub y is increasing because it favors the direction of gravity. So that's another important point to make. Next, the variables. These are your other best friends when you are dealing with projectile problems. So we have the x variables here. First, we have the v sub x, which is the horizontal displacement. Take note that this horizontal displacement is not specifically referring to the range. It's not necessarily the total horizontal displacement. We actually use the term range, and we use r to represent the total horizontal distance covered by a projectile. But take note, students, that when you say d sub x, it can be as short as this. It depends on what you're analyzing in the problem or what you are asked to solve. It can be from this point up to this point only or whatever. The problem could say, solve for the horizontal displacement after 3 seconds or when time is 3 seconds. So d sub x could be the horizontal displacement between any 2 points in the entire trajectory. If you're referring to the total horizontal displacement, you can use the term range of the projectile because it refers to the total horizontal distance covered from start to end point. Next, we have v sub x. Horizontal velocity, again, it just describes how fast the projectile is moving or progressing along the x-axis. Meaning to say, if this is you standing right here, v sub x or horizontal velocity is how fast does the projectile get farther away from you from where you are standing in terms of horizontal distance. So that's v sub x. And then time is the time considered in the problem that the projectile is airborne. So time may be, it depends on the problem. It could be the total time traveled. It could be the total time to get to the maximum height. It could be the time taken to get from this point up to this specific point. So yeah, you have to analyze the problem and make sure that you know what time you are dealing with whenever you put or you write down your given in the problem. So it's gonna be clearer when we solve actual problems, don't worry. And then for the y variables, then, of course, we have d sub y, vertical displacement. The vertical displacement could be this. It could also be this. But it can also be this vertical displacement. We're not sure unless we have a specific problem. But the point is that the displacement along the y-axis can be any chosen 2 points in a projectile problem, and you represent it with d sub y. And then a sub y is the acceleration along y-axis. Again, it's negative 9.8 meters per second squared because of the gravitational effects. And then time, again, it has the same definition as this. And then initial vertical velocity. Yeah, by the way, be familiar with this. The zero here is actually read as not. That's spelled as Nought. So it's not a letter O. Do not be confused, just to clarify this one. It's actually zero, meaning to say at zero time, this is the velocity. So that's why it's called the initial vertical velocity, because this is the velocity when time is considered as zero. And then the v sub y is the final vertical velocity. Also take note that the initial vertical velocity isn't necessarily the one at the starting point. And final vertical velocity is not necessarily the velocity at the final point. What I'm saying is that if you have a projectile problem, the initial vertical velocity could be this. Because maybe my concern is only to analyze the downward motion of this particular projectile. Because that's what the problem is concerned about. Or maybe that's the given variables in the problem are mostly located or situated in this particular part of the trajectory. And when that is the case, I might consider this as my initial vertical velocity, and my final vertical velocity could be this one, right? So these initial and final vertical velocities are arbitrary velocities, meaning to say they're not necessarily at the very beginning of this path or at the very end of this path just because they say initial or final, okay? So these are just any 2 points in the trajectory that you are particularly analyzing or that the problem is particularly concerned with. So you can set the initial and final vertical velocity to be this or that point, depending on what you need to solve for in the problem, and depending also on the given variables in the problem. Okay, so don't think of them as fixed positions or fixed options in the problem. They can be at any point in the trajectory, as long as you know what you are analyzing. Okay. Also, here's the summary of the key concepts. So please feel free to pause the video to write them down or maybe take a screenshot. These are more key concepts. Okay, so that's actually the end of this video. In the next videos, we're gonna solve actual projectile problems, and they will really strongly rely on what you have learned in this video. So make sure that you watch those sample problems for you to really learn how to solve projectile problems. That's all. Bye.